Okay, so this time we have another tank reactor problem. This is our CSTR, our continuously stirred, and we're also assuming well stirred tank reactor. And this time we're going to be solving for a temperature and concentration profile where this reaction is taking place with a cooling, I guess a coolant, I don't know how you want to call it, like a cover, I guess, as well as a exothermic reaction. So we'll have to take into account those two parameters for our energy balance. So that getting started, I'd like to try something new here. Got a whiteboard, so this will be fun. Hopefully it still picks up, yeah? Okay, perfect. So go ahead and draw our little reaction over here. Guess you can't see that well. Let's go here. So we have our reactor. We can make that better. We have our reactor. We have a Q in and Q out. Hopefully you can see that pretty well. Oh, good enough. And this is covered by a cooling jacket with some temperature in the coolant. And we're saying this is well stirred. We can make that better. And I believe the term is used for a overflow reactor, in which case we assume that the Q in equals the Q out because there's no other way for the liquid to escape. So in this, we're saying the Q in is equal to the Q out. Again, there's a concentration of some reactant concentration A going in. We have our initial concentration, Ca naught, or as I guess in the problem we refer to it as Cai initial, and we also have Ca out, which we are again saying that the Ca out, because this is well stirred, the Ca out must be equal to the concentration of A inside the tank. So I'll just say that is Ca. I don't know if you can see that, probably not, it's too small, but I'll probably erase this and, well, I'll just write big over here. Some other parameters we have in our equation, what else do we have? So I said coolant jacket, some temperature coolant going in, and some temperature coolant coming out. The problem doesn't actually state that it's changing. I think we're provided a T equals 0 of the temperature of the coolant. So we're assuming this remains constant throughout in steady state. And actually after T equals 0 is when we'll change it, and you'll see that when we're coding. But for now, we're saying that the temperature of the cooling jacket remains the same in and out, and the only way we can do this is with an assumption saying that the cooling jacket, the flow of the temperature of the, I'm assuming water going in, must be extremely, extremely high so that the temperature does not change as a result of in and out. All right. Other than that, I did mention we have a reaction going on, so there is a K constant over here. And that K constant relates to Arrhenius law, and I might switch to the iPad for that as I go on and aside about Arrhenius law, but keep in mind that parameter as well. I think we have everything labeled for now. Remember, this is a reactor, so let's probably do the mole balance over here. Yeah, so starting with our mole balance, you probably can't see that, but that says mole balance. I'll try to write bigger here. So our mole balance, well, we're interested in our differential equations. Remember that we're going to be using solve IVP and collaboratory with Python to solve the right-hand side of our differential equations. In this case, it'll be two of them. Remember I mentioned we're interested in the concentration profiles and the temperature profiles. So we'll try to do a mole balance and then isolate our derivative next. So we have what we're interested in, our concentration of A. Is that big enough? Maybe we can go bigger. Our concentration of A, and again, this is a derivative with respect to time. Since this will be changing, what with the reaction going on. And then remember that, I mean, hopefully it's okay. I can erase this. I guess I'll erase it as I make time or make room. But remember our units for concentration are moles per volume. In this case, I believe our volume is liters at the top. So liters, moles per liters, and then also time with our, I don't know if you can see that. So moles per liter per time, and I believe our time is in minutes. So go ahead and do that. So since we had moles per volume, since we're doing a mole balance, we want to get rid of that volume parameter, that liters, so we're going to multiply by volume like so. And this must be equal to, well, remember it's a mass balance, well, I guess mole balance for unit-wise, more specifically, I should say. So that is in, in minus out minus what the reaction is, I guess removing or consuming is probably the right word. So reaction consumed. So the addition of all of those parameters will give us what is the concentration of inside the tank. So I guess what remains. So remain equals in minus out minus what the reaction consumes. So in minus out, well, what do we know? We have a volumetric flow rate. So that is Q. And the Q, remember I said Q in equals Q out, and that was because we made an assumption that the tank is well stirred. So if Q in equals Q out, we can factor out this Q in the in minus out parameters. So we'll have in minus out. Well, what's going in? Well, we have our initial concentration going in. That is CAI minus our concentration in the tank, which is CA. Hopefully it's still got room here. I'll probably squeeze it under here. Or you know what, I guess I'll rewrite it. Yeah, I'll go ahead and rewrite it so we can kind of see everything. So volume times our change in concentration of A with respect to time is equal to our volumetric flow rate, which is in liters per minute, and the difference between, multiplied by the difference between our initial concentration, CAI, and our concentration in the tank. So that's our in and minus out parameter. What's next is we have our consumption of the reaction. Remember, we have a rate constant K, and this is relating to Arrhenius law. But if you remember sort of from a, I don't know, general chemistry, we have our rate constant times our concentration of A, and that is how much concentration of A is being consumed. Remember that we have to watch out for units, so we can actually break this down. Our volumetric flow rate is actually, so volumetric flow rate, volume per second, we have liters, let's make this bigger. We have our liters per minute times our concentration, moles per liter. So now we have moles per minute. Same thing over here with our concentration. We have volume. Well, you can just say, again, liters, this is volume times our molar flow rate, or I'm sorry, our change in moles per second, or per time, which would be per minute. So change in moles per liter and time. So again, we're focusing on moles per minute, moles per minute. This means this has to be moles per minute as well. Well, the units for K, I believe they're given in the problem, or I think that's a frequency factor. And again, I'll go into more of this on the iPad with the OneNote, but with Arrhenius law, we can kind of break down our units for K. Remember, this is a first order reaction. How can I tell? Well, if we break down the units, you'll see that in a first order reaction, the units for K are 1 over time, and that is the same unit as its frequency factor. So as we know that, well, our K is 1 over time, our minutes. And note, this K is different from the K naught over there. That K naught comes from, again, Arrhenius law, which I'll go into later. So 1 over minute is our rate constant, and then times CA, again, moles per liter. Well, you'll notice that we are missing a unit removal here. We need to get moles per minute, and the only way to do that is to multiply by our volume. So we're going to go ahead and multiply by volume just like that. Okay, so this is our molar balance here. Again, solving for the right-hand side, we have we're going to isolate for our derivative, so we can again solve the right-hand side. So I'm just going to be simply dividing by the volume, and dividing by volume, we simply have Q over V, and here we divide by volume, we get rid of our volume here. So this is our final expression for our molar balance. So that's what we'll use to solve for the right-hand side in our Python function and solve IBP for the concentration profile. So for my sake, I'm going to write it up here, pretty small, but yeah, since we're kind of need to make room for the other differential equation, the temperature. So we had dCA dt. Yeah, you can't really see that, so I'll just go ahead and copy this down real quick, just for my sake. Yeah, it is kind of hard with the camera angle here. So KCA, and hopefully this has been out long enough. I don't think there was anything else I needed to add to this. Well, I guess I should mention now that we're talking about the energy balance now. Remember what I said earlier, we have an exothermic reaction. This exothermic reaction releases heat to environment, so it's actually written as a negative over here. But it's a little misleading since the environment is our reactor. So what that means is we're actually adding heat to our system here. So we'll be adding that negative number, or you can say subtracting that negative number so it's positive, or just add knowing that it's energy added to the system. So yeah, I don't think I really need to add anything else. Oh, I guess the other component I'm missing is the cooling jacket. So with the cooling jacket, that'll be a heat loss to the system. As you can tell, it's a cooling jacket. Our tank will have, I guess, a temperature that's higher than our cooling jacket temperature, and that will be the driving force that we multiply with our overall heat transfer coefficient, and that will be what represents our energy loss with heat loss to the cooling jacket. So that's why we had our cooling jacket here. Hopefully that makes all sense. Hopefully that all makes sense, and I'll just go ahead and erase this so we have more room. Up next, so energy balance. Energy balance. You know, professors make it look easy, huh? Okay, so energy balance. Well, remember our change in internal energy is equal to Q minus our heat minus our work done by the system. And remember that, well, for our reactor, we have no work done, so it's simply just whatever Q is. So Q is our heat of the system, and remember we break that down into the mass times the specific heat times a change in temperature. If you remember going back to my previous video, we said our change in temperature is simply just our temperature that we're given minus a reference temperature. And if we say that our reference temperature is 0, we can just say that our change in temperature is just the temperature itself. Okay, so breaking down what we have, well, this is a reactor. We have a volumetric flow rate. So what we want to define for the left-hand side for our mass will be the density. Did I say that right? Density times the volume, I should say, excuse me, times the volume to get our mass, and then we have a specific constant, water, I believe, and then our temperature, which is what we're interested in. That will be the differential. So saying that again, we have our density times our volume of our reactor times our specific heat constant and our change in temperature over time. So breaking down units, just so we can get a clearer picture, density is grams per liter, volume is liters, and our specific heat constant is actually joules per gram per Kelvin, and now we have Kelvin per time, which is minutes. Breaking down our units, liters cancel, grams cancel, Kelvins cancel, and you're left with joules per time, which we know is just watts. Cool, so this is what we want to end up, our units in watts. So solving for the right-hand side, well, remember in minus out, we have our exothermic reaction, adding heat, and then our coolant cooling jacket, removing heat. So what we're going to do first, in minus out, well, remember what I said earlier, our volumetric flow rates are the same. So I'll have a Q here, and our water coming in, or whatever the liquid coming in, has two different temperatures. We have our temperature initial, and minus our actual temperature in the reactor, which we denote as T. Remember our units here, Q is a volumetric flow rate, so that's liters per minute. And now we're left with times Kelvin, our temperature. So clearly you know we're missing some parameters here. So what do we know? Well, we have to convert a volumetric flow rate to mass, we need to use our density. Density gives us grams per liter. And we know grams is used by another parameter, specific heat. So multiplying by the specific heat will give us more understanding of this parameter as a whole. So joules per gram per Kelvin. Now we have joules on the top, so grams cancel, liters cancel, Kelvin cancels, and now we're left with joules per minute. Awesome. What's next? I probably should have kept that up, but we might run out of room here, so just leave the bottom open for now. I said in minus out, we can do our heat of reaction next. So again, you could write this positive or negative, but remember to be consistent in the way you interpret this. But remember, we have a heat of reaction. I think they use that delta H. I'm not sure. Negative delta HR, heat of reaction. So I'll just denote it like that. Remember that this is technically negative written in the units over here, but since it's an exothermic reaction, again, we are giving heat to the system. So it's actually a positive addition to our energy balance. Well, I believe the units for HR are joules per mole, and we want to get to joules per minute. Well, remember, we already have an expression showing what our reaction is represented by. That was in our mass balance, the K times Ca times V, our rate constant times our concentration of A times our volume, and that's exactly what we need to put here. So K is 1 over time, which we said is minutes. Ca is our concentration of A, so moles per volume. And all that's left is to get rid of our volume, so we multiply by volume. And that will give us joules per minute, which is what we want. I have a blue marker here, but I'm not really using it. Should have used it earlier with the coolant temperature. I guess I could use it here now with the UA. So again, denoting our UA, our overall heat transfer coefficient times area. Yeah, let's just write that. I'm going to go ahead and go to the next line here. So put I don't know how you want to do this, like an ellipses. So we'll go down here. We have minus because we are losing heat to our cooling jacket. So that's why it's a subtraction from our energy balance. So remember our UA, overall heat transfer coefficient, times area. And I believe, well, let me just check now. The units for UA are joules per minute per Kelvin. So joules per minute per Kelvin. So breaking down the units, well, we already have joules per minute. All we want to get rid of is Kelvin, and make sure we are doing this by the driving force. So the overall heat transfer coefficient times area times the driving force is what we want to express with our subtraction in this parameter. So this will be times temperature. However, this temperature will be between, as you can guess, our temperature in the reactor, which I erased, and minus our temperature in our cooling jacket. And if we kind of think about how this makes sense, if the temperature in our reactor is higher than our temperature in the coolant, well, this will produce a positive number, and the positive number times a negative number, we're subtracting that energy loss from the cooling jacket. So that's why this makes sense. So now that we have all our parameters, all the units check out, again, we're going to isolate for our derivative once more. I might just bring down this more so you can kind of see all the divisions by rho VC as I bring these down. So I'm just going to make more room up the top. So just copying this down. You know what? Might be good to use another marker, so I'll go ahead and do that. My little pack here stored my markers. Let's go red. Okay, so again, we're just dividing by row VC. Oops, doesn't want to stand up here. Okay, row VC. So we're just dividing across to isolate. So row VC. Oh, that's nice. Row VC. Divide across. So dividing by row VC, we'll see that our volume actually cancels out here, and our density. So I can get rid of our row. Oh, that's the wrong one. Row and C. Row and C. So now we're just left with volume. I'll just go ahead and rewrite volume right here. Hopefully that shows up pretty good. And again, row VC, so density, volume, specific heat. You can see our volume is in this component, so we'll go ahead and take that out. And all we're left with is our density times our specific heat. And then coming down here, none of these terms show up, so we're just going to divide all across row VC. Awesome. I don't know the best way I think I'll write it up right here and probably just leave it up. No, I think I need to switch my camera angle actually, so I'll take a picture of it, I guess. So we have our entire expression, change in temperature over change in time, and copy this mostly for my sake. So this is the expression we're going to type into Python and Collaboratory as we code this out and actually solve and plot this out actually in Collab. So CA over row C and minus, getting to the point where you can't see it, but it's okay. So UA, overall heat transfer coefficient, times our driving force, with difference in temperatures between our temperature in the reactor and our cooling jacket, divided by rho, come on, rho, volume, so density, volume, and specific heat. Yeah, go ahead and save that. You know what? I think I can actually take a picture on my iPad. I'll go ahead and do that. So, insert camera and something like that. What is happening? Okay, I think we got it. Okay. Go ahead and put that in, and I'll switch over to this. Yeah, nice. So that's our picture. We'll go back and reference that when we can. I'll probably have to switch over this camera, so get to see some behind the scenes, I guess. Like so. Well, I'll just pause it and reorient this and pause. Okay, so while we're here, I figured now's the good time to mention the Arrhenius equation I was mentioning before. So that was, remember our K is equal to, so Arrhenius' law or expression is K times or K is equal to, our rate constant is equal to K naught, our frequency factor, times exponential of the negative EA activation energy over R gas constant times temperature. And I guess a way we can kind of visualize what the meaning of this is, I guess I'll tell you up front, with a higher activation energy, this EA, the more sensitive a reaction will be. And we kind of see this, in a graphical sort of method or expression. So what I'm going to do is take the natural log to get rid of E. So I take the natural log of both sides. And what we're left with is simply an expression that we could use to graph our lines. So this is usually what you'll see. Hopefully this is familiar. And if you can kind of see, this is just an expression we use for our line. It's just a line. So let's go ahead and plot this up, not in code, but just here. So a way I like to visualize, well, y is the ln k, the natural log of k, and our x-axis is 1 over t. And if you notice, this is the inverse of temperature. So actually, as we move from one temperature to another, from right to left is actually an increase in temperature. So it's the inverse of what you'd normally think it is. So with that being said, remember that our EA over R is our slope. So the slope of the line, I remember I mentioned that a higher activation energy, aka a higher slope, has more sensitivity to temperature, and therefore you'll kind of see it has, well, let's just go ahead and graph this out. So we have arbitrary line, I don't know, very steep one, versus something very, let's stop it at something like that. And then versus something with a relatively not as steep, so maybe something like that. And we'll pick two arbitrary temperatures. Maybe I should have made this a little longer, so we'll go something like this. So we have some crossover here with our temperatures. I'll say this is arbitrary temperature 1, so 1 over T1, and this is another arbitrary temperature 2, 1 over T2, and now remember I'm saying we are increasing as we go from right to left. So this is an increase in temperature, and what we'll see here is the change in K. Remember, y is our natural log of K. So we have, let's start with our less steep line. We have a very, very small change in K. This change of K is, we'll call it K1, versus our change of K for something like our other line here, the more steeper line. Obviously, you can see that this will be a much bigger change of K for K2. So we see that K2 is greater than K1, meaning that our rate constant, aka our line for, I guess, our reaction for, I guess, the white line here for K2 has more sensitivity, and its rate constant changes faster in the same given temperature range versus the smaller brown line that obviously the temperature difference didn't really affect its rate constant that much. So again, our m, our constant here, is our m is our slope, and our slope here, with a higher slope, we have a higher activation energy, because remember that dividing by r is just a number, so eventually that slope is just a number. So yeah, I think that's all I want to say about that, aside for Arrhenius law. And also, I think one more thing is what I forgot to mention when I was talking about first order reactions. Well, I was talking about the units, so for first order, we have our rate is equal to our K, our rate constant, times our concentration, and this is to the first power because it's first order. While breaking down units, we'll kind of see why. So this is concentration, or molarity per second, is equal to our K, which we're going to find the units for, and also this is our molarity to the first power, so just molarity. And if we try to isolate K, well, we end up seeing that the molarity is canceled out, and we're left with 1 over seconds, or 1 over time, whatever parameter of time you choose to use in our problem. So yeah, that's how we know that K was first order, because of our units. And remember that this does change with the order of the reaction. Like, say if this was, instead of 1, it was 2, well, now our units wouldn't be 1 over second. Well, what would it be? It would be 1 over second molarity. Okay, so with all that stuff out of the way, let's go ahead and get back to our problem. Remember that we're going to be solving for this, plotting this out, and yeah, solving the right-hand side with self IVP. So I believe I actually, yep, I put out the I wrote out the units and all the parameters, the given constants, so that there's no mistakes when we go through, and less troubleshooting for me. So basically what I have here, remember importing our libraries. We have subplots for our graphs. We're going to be putting our temperature and our concentration profiles on the same graph, or not the same graph, the same row. So they're side by side, and then we'll also have from SciPy integrate solve by VP, and that's for our right hand side. And again, numpy as NP. I believe we'll use it for our e to the power for our Arrhenius expression for k, and we have all our constants. So let me switch over to that. Hopefully this is moving. Let's just check. Okay, we're moving. Awesome. And still recording and audio. Perfect. So again, I like to sort these out. I kind of had a little bit of trouble when I was practicing where I was mixing up the initials. So there's the difference between our initial parameters. I note them as ti, or with an I, and then versus when t equals 0, so right after steady state. And these are the parameters we'll use for our initial guesses in solve by VP. So let's see, what do we want to do first? Well, everything's already initialized, so we'll go ahead and define our function, our right-hand side. And remember that solve IVP requires our function to be have two variables, one that's the independent variable, time in this case, and then the other with our other independent variables. And this could be any number, and I believe last time we used to call it vec for vector, and we unpack that vector as, and this can be any order you want, but I will choose temperature and concentration of A to keep it consistent. Okay, so what we're probably going to want to do next is defining our expression for K, and this is our K naught. So K is equal to K naught times the, remember, numpy of E, so exponential, and it was negative ER divided by T. Remember, this ER is given to us as E over R, but if you put a division sign here, Python won't like that much, so to avoid any errors, we'll call it ER, and divide by T because the expression is negative ER, E divided by RT. If we have ER, E over R, we simply need to multiply by 1 over T, or just divide by T. So hopefully that's good. What else do we want to do here? I think I can try to do a split screen, perhaps. So we can copy down our equations. So I'll try to pause here and do that. Okay, so I think we have this. This should be pretty good. I think we have everything defined here, so let's go ahead and use our expressions that we derived. So I'm going to say the differential for our concentration of A with respect to time, I'm going to call that dCA, and that was Q over our volume, big V. Let me double check, yeah, Q over big V, our volume, times our difference in concentration. So we have concentration initially, CAI, C underscore AI, times our concentration in the tank, which we'll say is just CA right here. It's the one that's changing in the differential, so that's what we'll use. And this is minus our K rate constant, which we defined up here with Arrhenius law, and that is K times the concentration in the tank as well. Right after that, we have our change in temperature, just call that dT with big T. And then we also have our Q, our volumetric flow rate over volume. Once again, this is times our difference in our temperatures, so a T initial, and this is with a TI versus steady state. Remember, our right after steady state, we have T equals 0. So I guess it's technically right before, right after, however you want to say it. But this is what our initial guesses will be, or initial values we'll use for solve IVP, so we don't want to use that. We want to use our initial temperatures at steady state, so that's Ti minus RT, that's changing in our reactor. Initial to that, we have our addition of our negative heat of reaction. I believe we called this negative HR, so I'll do negative HR, is that lowercase? Yes. Times our K rate constant times our concentration of A in the tank divided by rho times our, I believe that's specific heat. So big C, yes. So again, that was the addition of our exothermic reaction. So exothermic, even though it's a negative number, we have to remember that this is a reactor or a reaction taking place in the reactor. So the heat actually goes to our reactor and it's being added to the energy in our system as we have defined here. And from that, we subtract our expression that we use for energy loss to the cooling jacket. Remember, it's our overall heat transfer coefficient, UA, and this is times our driving force, the temperature in our reactor, so that's changing, minus our temperature coolant. So I'm going to go ahead and plug this as T, temperature of the cooling jacket right after steady state, T equals 0 for now, but remember that this is actually wrong since needs to be changing as well. We can't supply our initial guesses right after steady state T equals 0 into our expression, as we'll have some different numbers that we'll be looking at. So that expression divided by rho times volume times specific heat. So let's double check here. Q over V, CAI, CA minus KCA, Q over V, TIT, and I think everything looks pretty good. Yeah, okay. So what we're going to want to return here, and I think we can actually swap over to just collab at this point. So I'll go ahead and do that. So switch over and full screen this. And yeah, we're going to go ahead and just return this. So return, remember that we had our vector defined as temperature and concentration of A, so we want to return them in the same order. And remember, we'll do this the exact same way anytime we unpack this vector, since it is two different components, we don't want to mix those up. So we want to return our temperature, our differential dT, and dCA. So hopefully we're good there. I had this open for a while, so I might need to rerun everything, possibly. I'll just go ahead and do that. Why not? So what's next? We have solve IVP. Remember, solve IVP takes a couple parameters. We have our function, so right-hand side, and then we'll have a range that we'll define. Remember, we'll need to define well, usually we put 0 to a t end. I believe it's 10 minutes in this problem. Yes, I put it here. So this is actually a little spoiler, but feel free to read that if you want to. So we have 10 minutes. Remember, our time is in minutes, so 0 to 10. And then that's our range. And then what's after that, we have our supplied guesses. So remember, these are our supplied guesses. So we want to put our guesses in the same order as we unpack the vector as before. So temperature first. So temperature at T equals 0. And our concentration of A at T equals 0, 0. And then what else do we have? Our method, I believe we changed this to, in a previous video, we saw that RK45 wasn't as accurate as Radu, so we're switching to Radu as our differential equation solver. And remember, the other thing we added was dense output, so we had a solution function that we could call for our T-plot. And we set this to true since it's set to false as default. And I think that's all we have. So go ahead and do that. Hopefully it doesn't yell at me. Yep, we converge. Perfect. We have a solution. So we'll go ahead and just call that solution function. And we'll need to define our t-plot here. So our t-plot, we're going to do linearly spaced points, np-lin space, 0 to t end. And we'll do like 500 points, why not? So then we'll shove that into our function so that it will calculate the times for all our temperatures and concentrations respectively. Awesome. So now if we just store this variable here, just to make things look neater, now we have, actually, let's clean this up a bit. So we're storing the variable as solve IVP, and then if we do the res solution, call the function at tplot, then we should have the same thing, and it just makes it a lot cleaner in one line here. And we're going to go ahead and unpack that, since remember, if I take the shape of this array, we should have, 2 by 500. And that's because it's um, temperature and concentration and the 500 points that we use here. So, and that's the corresponding temperature and concentrations that we got from our function. So I'm going to go ahead and unpack that as, let me move this up. We'll call it our temperature plot and our CA plot. Do I do underscore? I think I do underscore. No? I'm a little inconsistent here, but that's okay. I'll just do concentration of A plot. CA plot equals. So we unpack that vector or array. And now I think all that's left is to just graph this maybe. So yeah, we have subplots, perfect. So I'm going to go ahead and call this figure 1. Figure 1 is equal to make subplots, and I want to add 2 rows and 2 columns. Well, I should say 2 rows, or 1 row and 2 columns is what I want to say. So that way we have them side by side on the same row. Figure 1 dot add scatter, so we add our points. X is equal to RT plot, Y is equal to our temperature, and I think that's all we need for now. I'll call this temperature, and go ahead and copy this down. And then all we're changing here is CA plot, and we'll call this the concentration of A. Let's just call it this. So what else do we have? I think that's it. I think I might want to update the layout, concentration A. So figure 1 dot update layout. Oh, I remember it. We wanted to move the rows and columns. So row is equal to 1, column is equal to 1. And then this will just be same row, different column, so the second column. And the layouts width is equal to 600 and height is equal to 400. And the template is equal to Plotly Dark. Please work. Okay, here we go. So I mentioned why it was looking a little wonky here. I mean, we can try to interpret this, but for now, this is actually not what we want, since remember I mentioned that putting in our temperature coolant, let me make sure it's still recording. Yeah. So putting in our temperature coolant right after steady state doesn't make sense in our expression because that was the coolant at steady state. We actually want to say this is changing. So after the coolant temperature of the cooling jacket changes, that's when we get to see some more funky looking graphs. Well, let's kind of interpret this. Well, we have a very set steady concentration and temperature for our time period, and it looks like it doesn't really go anywhere until we reach this 10th minute. This could be a result of some errors, but if we interpret this correctly, we have a spike at around 10 minutes where the temperature skyrockets and the concentration plummets as a result of the reactant A getting consumed, and our temperature goes up due to that exothermic reaction. So now if we go back here, actually change it to our steps of what we actually want to see, and we evaluate everything, now we'll get to see not that. So I think we have a little error here. This is not the graph we want, so I'll go ahead and pause here and see what went wrong. Okay, I think I found our error here. Sorry about that. It seems like we always have an error whenever I do this, but simply just a subtraction. And remember, I guess I can pull it up. Oh, well, my Discord's not open. Let's see. I can do a split. Or I think I'll just full screen this if I can. Maybe. Sorry about this. Expand and remember, we had a subtraction in our expression for our mole balance, which is what we should have had. So just change that. Let's actually go ahead and view it with the incorrect coolant temperature here and see if that changes anything. What are we doing? This, okay. So, evaluate everything. So yeah, this is actually what it would have looked like before with the correct expression this time. So it looks like at steady state, well, at least with the coolant temperature not changing, we actually had a decrease in our temperature and an increase in our concentration. And it looks like that was due to a change from our initial concentration. So we decreased our concentration from 1 to 0.5. Let me make sure I'm recording that. Okay, so 1 to 0.5, and we had a change in our temperature of our reactor from, let's see, 350. So actually, our reactor didn't change. Our temperature of the reaction didn't change. Very interesting. Let me double check that. So 350, 350. Yeah, very interesting. Our temperature didn't change. So yeah, it looks like the decrease in the concentration of A had the major effect of decreasing the temperature. Maybe there wasn't enough reaction, but that's why we use the differential equation to model that and simulate that to see what we would actually get. Now, if we actually put 305, this isn't in the problem that's stated, I believe, but doing that, now we get our funny looking kind of oscillations. So very hard to predict this, as you can see, but that's why the simulation is so important. I mean, you would kind of expect to see, well, you could argue that an increase in temperature of the cooling jacket would actually increase the temperature of our reactor, but no. We are limited by our concentration of A, and as you can see, before we kept skyrocketing and our reaction kind of ran away, almost having a runaway reaction. Well, we ran out of concentration of A, plummeted to zero, and then now we have this oscillation where every time our concentration goes up just the right amount, our temperature skyrockets and then decreases that right away. So yeah, I believe this was all to our problem so far. Let me try to show this. Nope. So yeah, we derived the expressions for the material and energy balances, plotted that temperature and concentration profile after deriving it, and we had to account for this equation as well. Going forward, we had our plotting. Again, very basic, just solving for the right-hand side using solve IVP, and calling the solution with the function for our solutions at our given times for 10 minutes, and found this nice, funny, oscillating graph. All right, so that was all for this problem. Look forward to part B, whatever and whenever that may be. Thank you.